Hello everyone, and once again welcome to my channel. In this video we will try to understand some of the very popular concepts in Linux relating to process and process lifecycle. In short, we will be discussing about what are zombie processes, what are orphan processes, and what is the role of subreaper, or in general what is a subreaper in Linux. So these are a few of the most important and widely used concepts in Linux, which a Linux developer or a person working in Linux environment needs to know. So yeah, without further delay, let's get started. Okay, so what happens when a process in Linux decides to create another process? How does it look like? Under normal circumstances, let's say we have a process P1 and it wants to create another process P2. What P1 can do and what most popularly is done is P1 will call the fork library call. So it will call the fork library call, which again it's nothing but a wrapper on top of the clone system call. I've already made a video on this in past about process forking in Linux using fork and clone system calls. I will put a link to that video in the description. Let's say process P1 forks a child process P2. So now under normal circumstances, a well-behaved parent, what it will do is after creating the new process, the child process, in one way or the another, it will wait for the process P2 to complete. So what P1 will do is it will wait for the process P2 to complete using one variant of the wait system call. Process P1 will invoke the wait system call and it will wait for P2. Now there are several variants of wait. The form of wait which we will be discussing about in this video is the most basic form of wait, which is the synchronous one or the blocking wait call. There is a asynchronous or non-blocking form of variant of wait as well. What happens is that once P1 calls the wait system call or the wait function, the parent process will start blocking on this call and it will wait until P2 is done with its execution. So once P2 is done and P2 dies after his execution under normal circumstances or under any circumstances, what happens is P1 gets a signal which is called sick child. So the kernel sends the parent of P2 a sick child signal, and on receiving that sick child signal, wait wakes up, right? Wait wakes up and it extracts the exit status of the child process into a variable or into a memory location. So usually the blocking form of wait, what it does is it takes a integer pointer. So what's usually done is that a variable called int, let's say child status would be defined and wait would be parent would send the address of the child status variable to the wait function call. So far so good. So once this happens, the exit status of the child is extracted and stored into the memory location referred to by this child status pointer. So this is the normal flow that should happen or that happens when a parent process forks a child process and the child process finishes its execution. So if we see this thing in code, so here is a tiny C program in which we have a function called spawn. The spawn is called from the main function, right? Whenever you are dealing with process IDs, it's better to use the type provided by your system, which is the PID underscore T type def. And in spawn, what happens? The parent calls the fork system call. If the return value of fork is greater than 0, it means we are in the parent. Basically, we get back the child PID. We simply return the child PID. If not, then we know that if child PID is equal to 0, then we know that we are in the child. And this is a very simple child. What it does is that it waits for 20 seconds. It runs a loop where it simply prints I am child and it waits for 1 second and it keeps doing that. And at the end, it dies gracefully using a exit 0. So 0 is the status code with which it exits. Okay, and if the return value of fork is neither greater than 0 nor equal to 0 but is negative, it means the fork system call or the fork library call faced an issue and it couldn't get executed, right? In the main function, what happens, I have created a tiny if condition. So I have a global variable should wait, I have a macro defined should wait. So if should wait is equal to 1, then pretty much what I want is that the parent should wait for the child just like a normal parent. So I call the wait library call. Again, I keep saying library calls because these are all just wrappers on top of the actual system calls, and these wrappers are just defined in libc, right? So at this point of time, we can simply use the term system call and library call interchangeably, but what I actually mean is the wait library call, which actually invokes the wait system call depending on which variant we are using. Okay, so now what happens, we invoke the wait call and we pass the pointer to this child status, right, which I am defining here. Once wait call returns, what we do is we use this wif exited macro to check whether the child had a proper exit. If it had a proper exit, we simply extract the exit status of the child using this macro, which is wexit status, right? And we print it, or else we say simply that the child exited abnormally. So this is the normal case, and after doing that, what the process does, okay, let's get rid of this sleep as of now. I'll simply comment it out. So what happens is that after waiting for the child, once the child exits, the parent also simply returns. That's it. So let's see how this behaves. So what I'll do is I'll divide my terminal into two parts. Let me just zoom this as well. Okay, so I will first compile this code. Cool. What I'll do is I'll do a ps-ef and I'll grep for this process called zproc, right? And I want to do it continuously, so I know when the process gets created and when it gets destroyed. So I'll put the entire thing under a watch, and let's see. Okay, so we can ignore these are just the watch, it's just showing the PIDs of the watch commands and the grep, etc. And the other thing we know is that if I do a ps-ef head-10 or maybe 2, the second column is the PID and the third column is PPID. So these two columns are the most important columns that we'll be looking at, right? Okay, so let's start the watch command. Okay, so now let's run our code. Let's run zproc, and yes, so these are our two zproc processes. 10172 is the parent and 10173 is the child. Here you can see that for the PPID of 10173 is 10172. The child is running and the child exits. The moment the child exits, the wait system call on which the parent was blocking wakes up, and the parent also exits. Okay, so far so good. So at this point, it would be good to mention that this process by which parent uses the wait call to extract the status of the child is also known as reaping. So we call it in Linux, it's called the parent is basically reaping the child, which is it's extracting the exit status of the child so that the child can pretty much die peacefully, and the system can pretty much release all the resources being used by the child, because as long as the exit status of the child has not been extracted by the parent, the system will be using some resources to store that particular information, and also the PID of the child will be in use. So now the fun part starts. Let's see what happens when the child exits but the parent doesn't repeat or doesn't use the wait system call immediately on the child. So the parent waits for some time and then invokes the wait system call. So what I'll do is I'll make the child run for 10 seconds and I'll make the parent run for, let's say, 15 seconds. So I'll make the parent wait for 15 seconds. Then what I'll do is, after reaping the process, again I'll wait for another 5 seconds, let's say. So let's understand the flow first. So the main function spawns the child, right? The child waits for 10 seconds, and at the same time the parent is waiting for 15 seconds. So after 10 seconds the child exits gracefully with a 0 status code. But remember, the parent has not yet called the wait system call because it's still sleeping for 5 extra seconds. So at the 15-second mark, what happens is that it enters this if condition, it waits for the child. Theoretically, the exit status of the child should be available, so it simply extracts it and it sleeps for another 5 seconds, the parent, and it exits. Okay, so let's see what happens. So how this flow goes. Actually, I'll just, so that I get a bit more time to explain, what I'll do is I'll make this maybe 30 seconds, right? And I'll sleep for another 5 seconds or maybe 10 seconds, right? So at the 10th second mark, the child will die. The parent will be sleeping for extra 20 seconds. What we'll be interested in knowing is what's the status of the child, or how does the child show up in the process ps command output after the child has exited but the parent has yet not reaped it. So let's find out that. So what I'll do is, let me clear this up and let me compile it once again, and let's start it. So again, 11090 is the child and it's running, and now it ends. And this is the interesting part. Now zproc appears to be defunct, right? So the parent has not yet reaped the process, and during that window when the child has exited but the parent has not reaped it yet, that is not waited for it, the child goes into this state called defunct. And now once after the 30-second mark, the parent reaps the process is gone, the child process is gone. The parent was still waiting for 10 more seconds as per the configuration, and it exits. What happened here was, during that window, during that short window when parent was sleeping but the child had completed its execution but there was no one to reap it, its status showed up as defunct, right? So what is this defunct state? So this defunct state of the process is nothing but what we commonly refer to as a zombie process. So let's now try to understand what is a zombie process. A zombie process is a process which has finished its execution and has been shut down, but its parent process has not yet reaped it, or it has not, for some reason, not yet invoked the wait system call to extract its exit status. So if we try to understand this, what we'll see is that the zombie state or the defunct state of a process is a part of the process's natural life cycle. Why so? Because let's say it was a well-behaved parent, right? So I have commented out this sleep 30. What now the parent would do is basically the best case. Parent will fork the process and it will immediately start waiting for the child process. And once the child process exits, the wait system call will wake up and it will extract the process, extract the child process's exit status. So this is like an ideal scenario. But even here, if we think a bit deeper, let's say at T1, like at the time instant T1, the child process exits, and at the instant T2, as soon as the child exits, the kernel sends a sick child signal to the parent, and the parent uses the wait system call to repeat. So there has to be a very tiny delta between that T1 and T2, which is, let's say, T2 minus T1. And even if it is not visible to the human eye or to the PS command output, but still that time window, no matter how small it is, it exists, right? And in that time window, the process will be a defunct process or a zombie process waiting its exit status to be extracted by someone, right? So one more thing that we need to understand or we need to take into consideration here is that a zombie process need not mean that the process is orphan or that the process doesn't have a parent process, because the parent process might be very well alive but it's a not so well behaved parent, because it has not, let's say the parent is alive but the parent has not waited for the child or it has not reaped the child and it continues with its execution. Even in that case, the child process is not orphaned because its parent is very much alive but the parent didn't reap it. So what I'm trying to say here is zombie process need not always be an orphan process. So now why zombie process is not a very good thing, so let's understand that. So if I just run this program once again and let me just comment out this sleep 30 once again, so that the parent once again waits 20 seconds extra before reaping its child. And if I simply do a ps-ef prep zproc, and let's run it once again. So yeah, this is the normal run wherein the child is waiting for 10 seconds. It's just printing this thing. So this is the time when the child exited and once again it became zombie. Now if you notice that the child is still occupying or it's still holding back the process ID, which is 12449, the child of 12448. So this PID is pretty much useless right now because this PID cannot be reassigned to any other process. Okay, now it has been reaped, But what I'm trying to essentially say is, in case of a zombie process, its PID cannot be reassigned to any other process. And at the same time, the kernel is using some memory to store the exit status of the process. By exit status, I mean with what status code it exited, from which the parent can know whether it was a normal exit or it was abnormal exit, right? So all this kernel data structures still stays allocated for the zombie process, although it's not being used. And it will stay in the memory unless and until you restart your system, right? So it's basically a wastage of your system resources. So now just imagine a poorly behaved parent keeps on spawning children, like it keeps on forking children, and it doesn't wait for them or it doesn't reap them. So your system can soon have multitude of zombie processes, which means multitude of PIDs will become useless and won't be reassignable. If such processes are allowed to continue in this system and you keep on spawning zombies without reaping them, what will soon happen is your system will run out of PID and other system resources, probably like memory, and your system will crash, right? Because it won't be able to spawn more processes. If you can't spawn more processes, you pretty much cannot do anything in your Linux system. So that's why zombies are extremely bad, and the process should be coded in such a way that so that the sick child signal is trapped and the parent waits and reaps the child process. So now what happens if the process, after forking the child, it instead of reaping it or instead of waiting for it, it simply dies if the process exits itself. So remember, this time the difference is, right now in our current example, the process is not dying. The main process is not dying. It's simply waiting for 20 extra seconds without reaping the child process, during which time the child is a zombie. Now the new situation which I'm saying is that the parent process simply exits and the child continues to run. So let's try to simulate that and see what happens. So for that, what I'm going to do is I'm going to make this 60, like the child will stay alive for 60 seconds, and I'll kill the parent after 10 seconds, right? So that's the exact thing that we want to do. And okay, the other thing that I'll do is I'll make should wait to 0, so that the parent doesn't block on the wait system call. What I want is that simply the main process should fork the child process and it should quit. So now let's see what happens. So technically, since the parent is dying, the question we should be asking here is that what is the PPID of the child process that is going to be after the main process dies. Let's see that. So let me quickly compile it. And the watch command is still running. And the other thing that I'll do is I'll just bring in another terminal, and let me just zoom this a bit out as well. Yes, and okay, so that should be enough. Okay, let's start the program and let's see what happens. So that's child. It's gonna wait for 60 seconds. Right now the parent is right there, zproc 13539, and after the 10 seconds the parent dies, right? And now there is only the child process which is running. Initially the parent of this child was our main process, which was 13539. Now that, since that is gone, interestingly, now the PPID or the parent ID of the child is still a process, which is 2402, right? So somehow this child process got reparented to this new process called 2402. Let's see what is this new process. If I do a ps-ef grep, and the process ID is 2402. So this is the one. Remember, the second column shows the PID. So this is the process with PID 2402, to which the child got reparented. So the child process has now exited, and it also got properly reaped by this new parent, which is 2402. You know it's reaped properly because 13540 is no more appearing in this list. So let me just close this. So two interesting things happen here. If I just run it once again to show you, like the two interesting thing that happened is the child process, firstly, which was the child of the main process, once the main process died, it got reparented to this new process called 2402. And once the child is dying now, like the child didn't become zombie or nothing, like when the child died, it didn't become a zombie, which means the new parent process 2402 is a well behaved parent which knows how to reap its child. So let's understand what's this 2402 process is. So if you see, the 2402 process is nothing but /lib systemd hyphen user. So this is nothing but a systemd process. Now to understand what's this systemd process and why, firstly, the first question should be why out of all the processes, this child process got reaped to this systemd process, systemd hyphen user process. And secondly, why is this process so well behaved that it could reap stray children, which doesn't even belong to it. So to understand this, we need to take a step back and we need to understand the concept of init process or the PID1 process in Linux. So if I do a ps-ef, okay, let me just do it here. So if I do a ps-ef and do a head-n, let's say 2, sorry, it will be pipe. So our PID1 process has been init. So init process is always the PID1 process in Linux, right? Now the PID1 process in Linux has got several responsibilities. Like when your system boots, it starts a bunch of processes according to the various run levels that your system is currently now in. It also does the job of signal forwarding. When it receives certain signals from kernel, it simply forwards it to its child, and a lot of responsibilities the init process has in the system. One of the very important responsibility that init process has is becoming the parent of orphaned children in the process tree. So what I'm trying to say is that initially what used to happen, and to some extent happens now as well, is when a process becomes orphaned in the process tree or in the Linux system, that is the parent of a process dies, the kernel reparents the child process to the init process. So the init becomes a new parent or grandparent, whatever you say, of the orphan process. And the init process is built in such a way when the new process or when the child process it exits, the init process doesn't allow you to linger around as a zombie, but rather it reaps it. So let's just understand it visually once. Init process is like the ultimate parent of all the processes in the system, because all the processes is one way or the other spawned from the init process, because init process is the PID1. So let's say it spawns a process called P1. This again spawns a process called P2. Maybe P2 spawns P3, P4, P1 might have spawned P5. So it's just a random process tree. So what happens is, let's say now P2 dies, right? But P3 and P4 is still executing. Whenever P2 dies and P3 and P4 becomes temporarily orphaned for a very small window, what the kernel will do is it will make P3 the child of init, and same goes for P4. So both P3 and P4 will become the child of init. And when P3 will die, the kernel will send the child signal to the init process, and init will reap them. So in a way, it will also wait for this newly adopted children. So that's a very important, very one of the most important thing that init does, right? But then here what we saw is that when the process died, in our case, it didn't get reparented to init, but it got reparented to a process called systemd, right? Systemd hyphen user. So why that? Why did that happen? So for that, we need to understand the concept of something called subreapers, so which got introduced in Linux 3.4, like the kernel 3.4. In this case, what systemd process has done is that it has marked itself while getting created. Once the systemd process was created by its parent, what systemd process did was it marked itself as a subreaper, right? And now what is a subreaper is the next question. So with this setup, there is some certain issues, right? So let me just get rid of this diagram and draw a new one. Let's see why we needed subreaper and what made the kernel developers to come up with the concept of subreapers, right? So under normal circumstances, what usually a process tree might look like is, of course, we have the init process, and which is PID 1, and init process, either directly or via some other process, might have the session manager process under it. So what is the session manager process? The session manager process is pretty much the root process under which the session of a user is managed. So it will give birth to the all the other various processes which is required to run the session of a given user. So one such process is systemd slash systemd hyphen hyphen user. So it's a user session manager process used by systemd. So now the session manager or the systemd session manager gives rise to several other processes like P1, P2. One of the process among these process was our zproc process, right? So a very common technique in Linux to spawn daemons, like daemons are the long running processes which work in the background of the system, is by double forking. So in order to create a daemon, what usually developers do is that you first create a process, let's say P gives rise to another process, let's say C, which is the child, and the child gives rise to the daemon process, which is D. Let us assume these are the three processes, and what the developers do is that this intermediate process, like the child process of the actual process, what it will do is immediately after giving birth to the daemon process, it will die, it will kill itself, right? It will simply exit. And this entire thing works on the notion that once the daemon process is created and the intermediate creating child process dies, what will happen is that, so somehow this P is attached to the init process, right? So this entire daemon creation process works on the assumption that once the intermediate child dies, D will get attached to init, and init will then manage D. It will reap D once the work of the daemon is done, so that D doesn't become a zombie, but it has a valid parent. So this popular way is called double forking. Most of the daemons or several daemons in Linux are created using this double forking process, right? So let's fit this thing in our present setup. So let's say P1 wants to create a daemon, so it does double forking and it creates daemon process called D. So now D is not associated with any of the processes under the session manager anymore, but now D gets parented or D gets reparented to init process, because the intermediate child must have died and the daemon got parented to init process. This is also true for any other process which somehow for some reason dies prematurely, and in all such cases the child of such dead parent will always keep on getting reparented to the init process. For example, in our case, if in this setup, without a subreaper, without the concept of subreaper, zproc would have got reparented to init process, right? Now what's the problem here? The problem is the systemd session manager, as a session manager, needs to know all the processes that are dying under it and that are being daemons under it. So it needs to keep a track of all those processes. When a parent dies, it needs to keep track of the child process. If needed, it needs to extract the exit status of the child process so that it knows which process exited, what was the reason of its exit, and things like that, whether it was a normal exit or it was an abnormal exit. So all these things the session manager needs to track. Also, what are the daemons that are currently running in the user session? Why? Because it needs to know what daemons the user is creating, it needs to manage them. So all this responsibility falls on the session manager. With the current scenario, with init becoming the parent of all the orphan processes and all the daemons, this is something that the session manager cannot do, because all the orphan processes in this setup will get reparented to init. So session manager won't be able to track the processes fully under it. So in order to solve this problem of orphan processes and daemons getting reparented to the init process, what was done was the introduction of the process type called subreaper. So on and from Linux kernel 3.4, what a process can do is it can mark itself as the subreaper. So in this case, what happens is session manager would mark itself as a subreaper, right? Any process can become a subreaper, and to do that, the process just needs to call prctl2 system call, and it needs to provide a certain constant or certain macro to that function to mark itself as a subreaper. So with this new concept of subreaper, what happens in the present kernels is when a process dies. So let's say, let me just make some space. So let's say session manager has spawned P1 and P1 has spawned, let's say, P2 and P2 has spawned P3. Cool. So now let's say P2 dies, P2 exits and P3 is still running. Okay. So now what the kernel will do is the kernel will search in the process tree for the nearest process or the nearest grandparent, which is a subreaper. So if we follow this process chain, the nearest process which is a subreaper is the session manager. So what the kernel will do is instead of reparenting to init, it will reparent it to the session manager. And that's the reason we saw that instead of getting reparented to init, the zproc process, let's say this P3 is nothing but a zproc. So the zproc process would get reparented to the session manager. Let's say there was another process called P0 somewhere over here, and let's say that had marked itself as a subreaper. Then instead of reparenting to session manager, kernel would have reparented P3 or zproc to P0. So that's the use case of subreaper. So usually critical processes like the session managers or any daemon managers, they would mark themselves as the subreapers so that they can keep track of all the daemons and the orphan processes under themselves. So that's the utility of the subreaper process and the init process. So what happens if a system doesn't have any processes, or let's say a process chain doesn't have any process in its ancestry which is marked as a subreaper? So what happens then? So what the kernel will do is, if it can't find any process in a chain which has marked itself as a subreaper, it will fall back to reparenting it to the init process. So that's how the init and the subreaper relationship works. And this is extremely important. This entire concept of reaping a process or reparenting an orphan process is extremely important, because otherwise, as I mentioned, if you allow too much zombie processes in a system, then it would hog your resources and soon your system might become unusable. So this entire thing, or this entire concept of zombies and reaping, is very important in the Docker world or in the world of containerization, because in containerization often what we attempt to do is that we create a simple script, let's say any web server or any process that we want to run inside a container. We simply create a Docker file, and in the cmd command we start that process, right? But that is actually not a good thing to do. The reason is this same concept of zombie. When you start a process inside a container, that process becomes PID1, right? And since it becomes PID1, if the underlying OS image that you are using for that container is Linux, and if your process becomes PID1, the OS image will take it for granted that the PID1 process will perform all the duties of an actual PID1 process, which your process might not be aware of. So what I'm trying to say is that, let's say you want to containerize a process P, and in your Docker file you do a cmd and you somehow start P with some arguments and you run the container. So what happens is that if you do a PS, it will show that this P process becomes PID1, right? And the moment you do that, the OS thinks that it knows how to reap orphan processes, it knows how to do all the duties of a PID1, it knows how to forward signals and all those things. Now let's say your P process gives rise to number of children, right? Like P3, blah, 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 and several other children. Now what happens? Let's say P1 is a poorly coded process, and what it does is P1 simply dies without waiting for its child processes or waiting for its children. So since P1 has died, and P4, P2, P3 either is still going on or they might have exited as well. But since P1 didn't wait for them, they either become orphan processes or they become zombified orphan processes, right? So what happens is OS image, what it will try to do, it will, since P1 is dead, it will try to reparent them to P, right? Expecting that P will reap them and P4, P2, P3 won't stay as a zombie process, but that doesn't happen. What happens is P4, P2, P3 continues to persist in the system memory as zombie processes. And since P4, P2, P3's PID is also actual PIDs in your system, you are once again losing your PIDs. If you continue this to happen, your Docker container might soon run out of memory, or even worse, if you are running many such containers on your system might run out of your memory. So yep, that is why these concepts of zombies, orphans, and init process, subreapers are so important, because they allow you to manage your processes properly without your system suffering from resource wastage or resource hogging. That is it for this video. Hope you guys enjoyed this video, and see you all soon.